everyone, today we're going to be learning about curve sketching using derivatives. So first of all, let's go over briefly what and how we're going to do this and also why. So curve sketching with derivatives is pretty much what it sounds like. It's sketching a graph based on the knowledge we can obtain based on derivatives. So we'll be using the first derivative test to find critical points and also increasing and decreasing areas. Or we might actually use the second derivative test in some cases to determine where something is concave up or down. We will also use, in some cases, other knowledge, although we'll be trying to avoid it since we're learning how to do this with derivatives. Even whether a function is even or odd, which determines end behavior, positive or negative, which also determines end behavior, is the number of zeros and where they're located to find the x-intercept, which will help us graph it, and other discontinuities such as holes, jumps, and asymptotes, both vertical and horizontal. So why are we learning this? What's the point? Well, if you don't have a graphing calculator available, derivatives are a fast and easy way to find trends, especially from a given function. It also is helpful to make predictions and support claims you make using data. And functions are everywhere in the world, so being able to understand them is essential, and derivatives can help with that. So let's go over how to do this with a first example. So we start off with the function given to us, x squared plus 5x plus 6. And usually the problem will say, draw a detailed sketch or curve of this. So what I like to start with is finding the zeros, because you'll do that before taking the derivative. So by factoring out, we get x plus 3 times x plus 2. And those zeros, once set equal to 0, will be x equals negative 3 and x equals negative 2. So we have to keep those in mind. Next, we're going to be finding the first derivative of the function, which will end up being 2x plus 5, derived from that. And then we can determine whether it's increasing or decreasing at different intervals by choosing a number less than the critical point, which we'll go back and we'll find the critical point by setting the derivative, the first derivative, equal to 0. So we will get negative 5 over 2 because you'll subtract 5 divided by 2. And then we'll plug it into a line and we'll take a number less than and greater than the critical point and plug it back into the first derivative. So if you plug in negative 3 into the first derivative, you get negative 6 plus 5 equals negative 1. And if you plug in 0, 2 times 0 is 0, plus 5 is positive. So since it's decreasing and then increasing after this point, we know that x equals negative 5 over 2 is a minimum, and that's important to keep in mind. Then if we plug in negative 5 over 2 into the original function, we'll get negative 1 over 4, and that lets us know our minimum value of the function. Now, taking all this knowledge, we're going to graph it, and since we know that negative 3 and negative 2 are the zeros, we will draw a point on there where y is 0. Then we know that negative 2.5, coming from negative 5 over 2, is the minimum, and it's negative 1/4 is the y value. So we plug that in, and then we know it's increasing on either side because it's a parabola that is even, which means both sides are going to go up or down, and it's positive, so we know it's going to be positive. So that's a pretty simple example. Let's move on to the next one. Here we have a cubic function, so in order to find the zeros, you have to factor out x squared. You get x squared times x minus 3, so x equals 3 and x equals 0 are the zeros. Now we're going to apply the same method. We're going to find the first derivative, which will end up being 3x squared minus 6x, derived from there. And if you set that equal to 0, you get that x equals 2 and x equals 0 are the points you have to watch out for. They could be maxes or mins or stationary points. Now we are going to use the second derivative test to determine whether it's concave up, and therefore if it's a minimum, or concave down and a maximum. So to find the second derivative, you simply take the derivative of the derivative you already found. So here we'll get 6x minus 6, then you plug in the critical points you found earlier, so 2 and 0, and if you plug in 2, you get 12 minus 6 equals 6, which is positive, which means it's concave up at x equals 2, so that is equal to a smiley face. And then, if you plug in 0, you get that it's negative 6, so it's negative concave down at x equals 0. and that will be our maximum because the slope is decreasing the entire time, creating a maximum. And since we know that x equals 0 is one of the zeros, we already know the y value of that maximum point. But for the other minimum point, local minimum, we have to plug it into the original function, which is shown here, getting -4. Now, we'll also look at the end behavior, and although you could figure out end behavior just from the degree and whether it's even or odd, we're going to plug it in, and using the first derivative test, see whether it's increasing or decreasing afterwards. So if you plug in -1 and 3, you get a positive number, a positive value, and a positive value, meaning it's increasing on both sides. So if you plug all this in, now we use all this information to make a graph. So see how it's increasing on both sides, which we got from here, and then find our two x-intercepts, or zeros, 0 and 3, from here. And since we know that it's concave up at x equals 2, this is going to be a parabola-ish shape. And since we know it's concave down at 0, it's going to be here. And so that's how you solve this second problem, a little bit harder. Now the third and final problem we're going to be tackling is a little bit difficult as it involves a vertical asymptote, which we find by setting the bottom equal to 0. X minus 2 equals 0, plus you add the 2 to both sides, you get x equals 2 is a vertical asymptote. Now in order to find the first derivative of this function, we're going to use the quotient rule. The quotient rule is essentially low d high, high d low, square the bottom, and away we go. So this means you take the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. So when you simplify this out, you end up getting this, but the denominator is not important for our purposes right now. We're just going to set the numerator equal to 0, and then you can factor out a 2. You get x minus 2, x minus 1, and that ends up being x equals 2 and x equals 1 are our critical points. Now we're going to use a number line from the first derivative test, but it's important that we also keep in mind that there is a vertical asymptote at x equals 2, so we have to include that there. When you plug in some numbers, you get that it's increasing from -infinity to 1, and that it's decreasing from 1 to 2. There's nothing here because that's our vertical asymptote. And then from 2 to 3, it's decreasing as well. The function is decreasing. And from 3 to infinity, it's increasing. And if we plug in the critical points back into the original function, we can get the max and min. And then if we translate this all into a graph, we get the vertical asymptote at x equals 2, our minimum, 3, 9, and our maximum, 1, 1. Plug those in, and since we know it can't hit the vertical asymptote, it'll continue downward here forever and upward here forever. But it follows the positive, negative, negative, positive pattern, and so that is our final solution. I hope this helped, and I hope it helped you learn how to graph with derivatives a little better. Thanks, and have a great day.